So on Monday, we looked at hypothesis testing and we did a hypothesis test for means. Today, we're going to look at a hypothesis test for proportions. Situation I've created is a researcher is studying how often COVID-19 positive patients pass the disease to a spouse they live with. The researcher wants to prove it happens less than 75% of the time. In a sample of 300 COVID-19 positive patients, 210 of them passed it on to their spouse. Test at the alpha equals 0.05 level. So the first thing that we need to do when we encounter a hypothesis test like this is set up a null and alternative hypothesis. HO and HA. This is always based on what the researcher actually wants to prove. So what the researcher wants to prove is that COVID-19 positive people pass it to the spouse they're living with less than 75% of the time. That 75% should be a keyword that clues me in that this is a proportion test, not a means test. I also can see down here where I have a number out of the total. I never see anywhere in the problem that has a standard deviation listed, which I would need for a test of means. So there's a lot of different things that point me towards using P as the population parameter here as opposed to mu for a mean. So, sorry, I shouldn't have put that equal sign, doesn't belong there. But for the alternative, we're trying to prove it's less than 75%. That goes in as P is less than 0.75. Always your alternative is what the researcher is really trying to show statistical evidence for. Once you properly set the alternative, the null is always the exact same thing, just with an equal sign. So my alternative could have been less than like this, it could have been greater than, it could have been a two-tailed with a not equal to sign. In all three of those instances, I would have the same null, which is just P is equal to 0.75. Now that I have the null and alternative, I want to read the remainder of the paragraph and see if I can pull out any other key numbers that I'm going to need in my formula. So here I see in a sample of 300 COVID-19 positive patients. So the sample was 300 people. That's giving me a sample size, or N. I'm going to write down N equals 300. 210 of them passed it on to their spouse. That's giving me an X value, or telling me how many fit what I was looking for. Final thing I'm going to record is when at the end it says test at a 0.05 level for alpha. I want to know what that alpha is because it's going to impact how I run my test in the future. We're now at the stage where we want to compute the test statistic. The test statistic for a test of proportions is z equals p hat minus p0 over the square root of p0, 1 minus p0 divided by n. In this case, we have n identified. This p under the null is really what I mean by p0. So whatever this is that we set it equal to in the null hypothesis is what goes here in the formula, here, and here. The only thing that we don't have then is p hat, which we really need to calculate. P hat is based on x over n, and it stands for the sample proportion, or how many people within our study fit what we were looking for on a percentage basis or decimal basis, really. So we're going to set it up as the 210 that did pass it on to their spouse out of the 300 in the sample. When I do that division, I should get 0.7 or 0.70. Either one is mathematically the same. I can then set up my p hat 0.70 minus the p under the null 0.75 divided by the root of the p under the null 0.75 times 1 minus the p under the null 0.75 all over the n of 300. Most common mistakes that students make when they're setting up things like this the first time is accidentally putting this 0.70 in the bottom instead of 0.75. It is important. It's not going to change your answers a ton, but it's going to change them enough that they're going to be wrong. You need to make sure that the only time you're using p hat is in this place in the formula, and everything that's going in the root underneath comes from the null, because really the whole idea of this hypothesis test is we're going to look at the chance of seeing the sample data if we assumed the null to be true. So this bottom is basing the standard deviation in this situation on the null being true, not basing it on the sample data being true. Again, our goal is to capture what's going on in the larger population. So that's the first thing to consider. Make sure that it's the null proportion that's in the bottom of your equation. Second thing to consider is make sure you're putting this root in properly to your calculator. That 300 being outside of the root symbol is the most common mistake students make when they're first learning to put these into their calculator. So if we were in person, I'd be going up to you, showing you exactly where the parentheses need to go to make sure it's right. What you need to do is really just try this on your own and see if you're getting the same thing as me. If you're not getting the same thing as me, try and play around with putting in more parentheses. If it's still confusing, definitely just email me. Ideally, you can show me a quick picture of what your calculator looks like that you're putting in, and I'll see if I can tell what's going wrong. That said, if I do put this in properly, I should put into my calculator parentheses 0.70 minus 0.75 and parentheses divided by parentheses the root of parentheses 0.75 and parentheses new parentheses 1 minus 0.75 and parentheses divided by 300 and parentheses end parentheses. If I do that all correctly, I should get a z-score of -2, which if we go to 3 decimals, really should be recorded as -2.00. That represents my test statistic for this test of hypothesis. There's now 2 different ways I can go with that test statistic. The first way is I can look up this specific value in my z-table and find the probability. In this case, in my z-table, the row marked -2.0 and the column marked 0.00 should point me to a p-value of p equals 0.0228. Once I have that p-value, I need to look back to my alternative hypothesis to see how I need to use that p-value. Here, the alternative hypothesis is less than. Less than means it's a left-sided test, and I can use exactly the value that's in my table. So this 0.0228 is the test probability. I can then take the 0.0228, compare it to the given alpha value, in this case 0.05, and say which one's larger. Alpha is larger. Since my test probability is smaller than my alpha, I basically said if this thing has a 5% chance or less of occurring, I'm going to say that the null is wrong. This only had a 2.28% chance of occurring, so we're going to say the null is wrong. Our conclusion is reject the null. What that really means is we've officially proven statistically significantly at the 0.05 level that it is not correct that on average 75% of people living with spouses who test COVID positive pass it on to their spouse. Instead, we've statistically proven that it's true that less than 75% pass it on based on our sample. It's possible that we just got a sample of people who were less contagious, less than the whole population, and passed it on less often. That's what's represented by this 2% of the time we could have made errors. But because we have fairly convincing evidence, we can say that we're going to accept this alternative hypothesis at this level of alpha, and we've officially proven it to be true based on this sample. That said, there's a few different things I want to point out if there have been some slight changes to the problem. If instead we were doing a greater than test, and this says p is greater than 0.75, in that case, we need to take the value we get from looking up the z-score, do 1 minus that value to get the test probability. The 1 minus answer would be what we compared to alpha of 0.05. Even more difficult would be if this was a not equal to sign. If it's a not equal to sign, that means we have to see it as a two-tailed test and make the decision of next steps based on whether we get a negative or positive z-score. If we got a negative z-score like we did here to a not equal to test, we double the p-value before comparing. If we got a positive z-score, we need to do 2 steps. We need to first do 1 minus the p-value to get the right-sided value, then double that answer to get the total probability for the test, which we could compare to alpha. So there's definitely examples of me doing tests that work out like that in the classwork videos in the lecture. You want to look at them and see how it kind of changes when you have these different types of tests. That said, I also want to show you how to do this from a critical value comparison. So from a critical value perspective, the null and alternative is going to stay the same. This whole calculation to where I get -2 is going to stay the same. From there, it's going to be slightly different. I need to calculate what's the critical value for an alpha of 0.05 in a less than test. What that really means is, graphically, there's some value of z such that the probability to the left of that z is 0.05. That specific z would be negative 1.645. If I get a z-score that's more negative than that, it would fall in my region of rejection. So in this circumstance, I'm using this alpha value 0.05 and this alternative hypothesis being less than to line up in the chart and find this exact critical value. If you go into the lectures, there's a slide in there where it lists the only 9 that we will ever use in this class. The one for less than 0.05, greater than 0.05, not equal to 0.05. Less than 0.01, greater than 0.01, not equal to 0.01. Less than 0.10, greater than 0.10, not equal to 0.10. If you have those 9 in your notes, you will always be able to find where this rejection region starts just by lining up. What did I choose as my alternative? What did they give me as the level of confidence? In this example, now that we figured out where is the region of rejection, the next thing we need to do is make a comparison like we did here. The difference is for this comparison, we're going to graphically place this negative 2.00 where it would belong in this graph. It would be here, to the left of or more negative than z equals negative 1.645. If it had fallen here in the unshaded region, that's where we would fail to reject the null. When it falls here in the shaded region, that's when we have the conclusion, reject the null. Basically, by either method, we proved the same thing. We proved at the 0.05 level of significance that spouses pass it on less often than the 75% hypothesized. That said, there's reasons why you'd want to know how to do it both of these ways, and in the problems in Cengage, there's definitely ones that do it one way, ones that do it the other way. You need to be familiar with both methods. Let's see if there's any questions on anything I did. It looks like there are not, so I'm going to go ahead and stop the recording and remind you to email me if there's anything I can help you with in the future.